Welcome to this walkthrough of LeetCode problem number 553, Optimal Division. In this problem, we will explore how to calculate the optimal way to parenthesize a sequence of numbers for maximum division results. Let's dive in. In this problem, we are tasked with finding an optimal way to arrange a division expression using an array of integers called nums. The goal is to maximize the result of the division by determining the best sequence of operations. The output of our solution should be a string that represents the mathematical expression. For example, if there's only one number in the array, the output is simply that number as a string. If there are two numbers, the output is the result of dividing the first number by the second. When there are three or more numbers, we can use parentheses to specify the order of operations, and our task is to determine the arrangement that produces the maximum result. The input array can have a size between 1 and 10, and all numbers are guaranteed to be between 1 and 1000. This ensures that our calculations will always produce finite results. Let's look at some examples to better understand the problem. In the first example, the input array is 1000, 100, 10, 2. The output is the expression 1000/100/10/2. By grouping the numbers in this way, we ensure that the result is maximized. The calculation works as follows. First, divide 100 by 10, which gives 10. Then divide 10 by 2, which gives 5. Finally, divide 1000 by 5, resulting in 200. This is the highest possible value we can achieve through optimal grouping. In the second example, the input is 2, 3, 4. The output is 2/3/4. Here, dividing 3 by 4 gives 0.75, and dividing 2 by 0.75 results in approximately 2.6667. Again, this grouping gives the maximum value. Another example is when the input array contains just one number, such as 10. In this case, the output is simply the string 10, as no division is needed. The constraints for this problem specify that the array will always have at least one number, and all numbers will be between 2 and 1000. Importantly, we must use all the numbers in the array in their given order, and we are only allowed to add parentheses to control the order of operations. For instance, if the input is 5, the output would be 5. If the input has two numbers, such as 8, 4, the result is the straightforward division 8/4, which equals 2. These examples highlight how the rules differ depending on the size of the array. When the array contains three or more numbers, parentheses become critical for maximizing the result. For example, if the input is 6, 2, 3, we should group the numbers as 6/2/3. This arrangement minimizes the denominator, since dividing 2 by 3 gives a smaller value of approximately 0.6667. Dividing 6 by 0.6667 results in a higher value, around 9. In cases where the array contains the maximum size of 10 numbers, such as 1000, 100, 10, 2, 2, 2, 2, 2, 2, 2, the optimal solution involves grouping all numbers after the first into a single division operation. This ensures that the denominator is minimized as much as possible, leading to the maximum overall result. The key observation here is that division is not associative, meaning the order in which we perform the operation significantly affects the result. To achieve the highest value, we need to minimize the denominator by grouping all elements after the first into one combined division operation. The optimal strategy can be summarized as follows. If the array has only one number, simply return it as a string. If the array has two numbers, divide the first number by the second and return the result as a string. For three or more numbers, divide the first number by the result of dividing all remaining numbers sequentially. Parentheses are used to group these remaining numbers together, ensuring the correct order of operations and maximizing the result. To solve the problem of finding the optimal way to parenthesize a division sequence for maximum result, we first consider the brute force approach. The intuition here is to explore all possible ways to insert parentheses into the sequence. This involves recursively splitting the array into two parts and computing the maximum and minimum values for each split. By combining these results with the division operator, we can keep track of the maximum value and its corresponding expression. However, the computational cost of this approach is significant. The time complexity grows exponentially, proportional to the Catalan number, making it infeasible for larger inputs. While brute force guarantees correctness, the trade-off is its inefficiency, both in terms of time and space due to the recursion stack required. Now, let's take a closer look at the greedy approach, which leverages the structure of the problem. Division is not associative, but by observing the problem carefully, we realize that the optimal strategy is to divide the first number by the smallest possible denominator. This is achieved by grouping all remaining numbers into the denominator, which minimizes it and maximizes the result. For example, instead of sequentially dividing numbers, we can reformat the expression so that the first number is the numerator, and the product of all subsequent numbers forms a single denominator. This simplifies to nums 0 / nums 1 * nums 2 * nums and 1. The steps are straightforward. If there's only one number, return it. If there are two, return their division. For larger arrays, construct the result by appropriately formatting the division sequence. With a linear time complexity for constructing the result string, this approach is computationally efficient. The greedy approach, while efficient and elegant, does come with its own trade-offs. It relies heavily on the mathematical insight that grouping all numbers except the first into the denominator yields the optimal result. This insight, though powerful, may not be immediately obvious to everyone solving the problem. The chosen strategy is the greedy approach because it provides an optimal solution in linear time while avoiding the inefficiencies of brute force. The key realization here is that minimizing the denominator maximizes the division result. However, this approach sacrifices generality for efficiency. If the problem were to include additional constraints or operators, the greedy solution might not hold. Another consideration is the careful attention required to correctly format the output string to reflect the intended parenthesization. In conclusion, the greedy approach strikes the perfect balance between efficiency and correctness for this problem. By leveraging the mathematical observation about division order, it simplifies the solution to a linear time complexity with minimal space requirements. This approach is not only the most efficient but also straightforward, making it the ideal strategy for solving the optimal division problem. To tackle this problem, our goal is to maximize the result of dividing a sequence of numbers by carefully placing parentheses. The placement of these parentheses determines the order of operations, and as a result, the final value changes. For instance, in the array 6, 2, 3, dividing as 6/2/3 gives 1, but dividing as 6 divided by open parenthesis 2 divided by 3 close parenthesis yields 9. To find the optimal arrangement, one approach is to use a brute force method, where we generate all possible parenthesizations. This involves treating the problem as a recursive process where we divide the array at every possible index into two subarrays, left and right. For each split, we calculate the results recursively and combine them to evaluate all possible outcomes. This gives us the maximum result for the given array configuration. In our recursive approach, we first define a base case. If the array contains only one element, there's no need for further division, and we simply return that number. For the recursive case, we iterate through the array and split it at each possible index. This creates two subarrays, left and right. We then recursively compute the potential results for both subarrays. Once we have these results, we combine them using division to evaluate the outcomes for that specific split. Throughout this process, we keep track of the maximum result encountered using a variable max_result. To make this approach more efficient, we use memoization. By storing the results of previously computed subarrays in a dictionary, we avoid redundant calculations for overlapping subproblems. This significantly optimizes the recursion. The pseudocode demonstrates these steps, starting with a recursive function that checks the base case, utilizes memoization, and iterates over possible split points to compute and store the maximum result for each subarray. The pseudocode continues by iterating over all indices in the array to identify split points. For each split, the array is divided into a left subarray and a right subarray. The recursive function is called to compute the results for these subarrays, which are then combined using division. The result of this division is compared with the current max_result, and if it's larger, we update max_result. This ensures that, by the end of the loop, max_result contains the highest possible result for the given array configuration. To avoid recalculating results for the same subarray multiple times, we store the computed value in the memoization dictionary, using the tuple representation of the subarray as the key. Finally, the function returns the maximum result for the input array. The driver function demonstrates this process for the array 6, 2, 3, initializing an empty memoization dictionary and calling the recursive function to compute the optimal result. This approach is based on some key insights. First, the problem itself is recursive in nature. By splitting the array into smaller subarrays, we can solve these subproblems individually and then combine their results. The placement of parentheses corresponds to these split points, and each split creates new combinations of left and right subarrays to evaluate. Memoization plays a critical role in improving efficiency. By storing results for subarrays, we ensure that overlapping subproblems are not recomputed, which significantly reduces the computational cost. Additionally, it's important to handle base cases where the array has only one element, as no further division is needed. While the input is restricted to positive integers, we also ensure that division by zero does not occur. These insights form the foundation of our recursive and memoized approach to solving the problem optimally. To implement this algorithm, we rely on two primary data structures. The first is a memoization dictionary. This dictionary uses the tuple representation of subarrays as keys and stores the maximum result for each subarray as values. Its purpose is to eliminate redundant calculations by reusing results for overlapping subproblems. The second is the recursive call stack, which helps manage the state as the array is divided into smaller subarrays and the function calls are nested deeper. For the complexity analysis, the time complexity without memoization grows exponentially, as we explore all possible parenthesizations. This corresponds to the growth of Catalan numbers, leading to an O2 to the power of n complexity. However, with memoization, each subarray is solved only once, reducing the time complexity to O(n cubed). The space complexity has two main contributors. First, the memoization dictionary, which stores results for all unique subarrays, can require up to O2 to the power of n entries in the worst case. Second, the recursive call stack has a depth proportional to the size of the input array, resulting in an additional O(n) space requirement. Together, these space requirements define the overall space complexity of the algorithm. By balancing the use of recursive decomposition and memoization, we achieve a solution that is both effective and efficient for this problem. This solution for the LeetCode problem optimal division, problem number 553, is designed to maximize the result of a division sequence by strategically placing parentheses. First, the function handles edge cases. 1. If the input list nums contains only one number, the result is simply the number itself, as no division is possible. 2. If nums contains exactly two numbers, the result is straightforward: divide the first number by the second without any parentheses. For cases where there are more than two numbers, the optimal strategy involves dividing the first number by the result of dividing all subsequent numbers together. To achieve this, parentheses are placed around all numbers except the first. This ensures that the division of the subsequent numbers is maximized first, and then the result is used in the initial division. The code constructs the output string using Python's fstring for concise formatting. The map function applies str to each number in the list, and /.join concatenates these numbers with division symbols. This creates the correct sequence of divisions within parentheses for the latter part of the expression. Finally, the result is returned as a formatted string. This implementation is efficient with a time complexity of O(n), where n is the length of the input list nums, as it involves a single traversal of the numbers to construct the output string. Here, we begin by importing the necessary package and defining our solution class. Inside the class, we have the method optimal division, which takes an array of integers as input. The first condition checks if the array contains only one number. In that case, we simply return that number as a string since there's nothing to divide. Next, if there are exactly two numbers, the problem specifies that we should return their division without any parentheses. This is accomplished by concatenating the two numbers with a slash in between. For arrays with more than two numbers, the optimal way to maximize the result is to divide the first number by the result of dividing all subsequent numbers together. To achieve this, we use a string builder to construct the output string. We start by appending the first number, followed by /, which indicates the start of the division of the remaining numbers. We then iterate through the rest of the numbers in the array. For each number, it's appended to the result string, and if it's not the last number in the array, we also append a slash to continue the division sequence. Once all the numbers have been added, we close the parentheses to complete the expression. Finally, we return the constructed string as the output. This implementation ensures that the division order follows the optimal strategy for maximizing the result, as described in the problem statement. Here, we're working with the input array 1110, 2. Since the array has more than 2 numbers, we need to construct the optimal division expression using parentheses. First, the numerator is the first number in the array, which is 1000. For the denominator, we take the remaining numbers 110, 2, and divide them all together. To ensure the correct order of operations, we enclose these numbers in parentheses, creating the string representation 100/10/2. Finally, we combine the numerator and denominator, resulting in the expression 1000/100/10/2. This ensures the division is performed in a way that maximizes the result. The output for this input is therefore 1000/100/10/2. Now, let's consider the input array 2, 3. Since the array contains exactly 2 numbers, we don't need parentheses because the order of division is straightforward. The first number, 2, serves as the numerator, while the second number, 3, is the denominator. Combining these gives us the simple division expression 2/3. There's no need for further adjustments or parentheses since no additional numbers are present. The output for this input is simply 2/3. For the input array 5, there is only one number. In this case, there's nothing to divide, so the result is the number itself as a string. The output is simply 5. It's important to note that parentheses are only necessary when there are more than 2 numbers, as they help maximize the result by grouping the denominator appropriately. For example, 1000/100/10/2 yields 200, whereas dividing sequentially without parentheses would result in a much smaller value. The solution also handles edge cases for arrays with 1 or 2 numbers directly, ensuring both simplicity and correctness. Overall, the time complexity of the solution is O(n), due to joining the numbers to form a string, and the space complexity is also O(n), to store these intermediate results. In analyzing the time complexity of the solution, we start by considering the base cases. When the input list, nums, has only one element, the function simply converts that single number to a string. This is a straightforward operation with a constant time complexity of O(1). Similarly, for a list with 2 elements, the function constructs a division string in the format nums0/nums1. This involves 2 string conversions and 1 string concatenation, all of which are constant time operations. Thus, for these small input sizes, the time complexity remains O(1). Now, for input lists with more than 2 elements, the main computational work involves building the division string for the sublist nums1. First, the map str nums1 smiley face operation converts each number in the sublist to a string. Since the sublist has n1 elements, where n is the length of the input list, this operation takes n1 time. Then, the /.join operation concatenates these n1 strings using a delimiter. In the worst case, the time required for this operation grows linearly with the size of the input, making it O(n). Finally, the construction of the overall string, which formats the result as f nums0 /, is a constant time operation because it only involves adding fixed size components. Therefore, for larger lists, the overall time complexity of the solution is O(n), where n is the length of the input list. When it comes to space complexity, the memory usage primarily depends on the intermediate and final string constructions. The map str nums1 smiley face operation itself generates a generator, which is memory efficient. However, the /.join operation constructs a new string that requires memory proportional to the total length of the individual strings and delimiters. In the worst case, this memory usage is O(n). Additionally, the final result string, formatted as f nums0 / also takes up memory proportional to its size, but this does not add to the overall space complexity since it is still bounded by O(n). Importantly, no additional data structures are used in the process, so the total space complexity of the solution is O(n), where n is the length of the input list. To put this into perspective, consider the brute force approach to this problem. A naive solution would involve testing all possible ways to parenthesize the numbers in the list to find the optimal division. This would require evaluating all possible groupings, leading to an exponential time complexity of O(2)(n1). Such an approach quickly becomes infeasible as the size of the input grows. By contrast, the optimized solution takes advantage of the mathematical insight that the optimal result can always be obtained by dividing the first number by the result of dividing all subsequent numbers together. This eliminates the need for combinatorial exploration and ensures that the time complexity is reduced to O(n). Mathematically, this efficiency is achieved because the map and join operations each iterate through the list just once, and string concatenation involves a constant number of fixed-size operations. Similarly, the space complexity remains O(n), dominated by the memory used to store the resulting string. Together, these factors make the solution both time and space efficient. When solving the optimal division problem, there are several common mistakes to watch for. First, not considering operator precedence can lead to incorrect results. Remember that division and multiplication have higher precedence than addition and subtraction. For instance, if you treat a/b plus c as /b plus c instead of /b plus c, you'll get the wrong answer. Another mistake is ignoring edge cases, such as small input sizes. For example, if the input array has only one element, you must return that single number directly. Similarly, for two elements, the result is simply their division. Incorrectly defining the base case in a recursive solution is another pitfall. Without a proper base case, your recursion might either run infinitely or return incorrect results. For instance, when the start and end indices are equal, you should return the single number in that range. Lastly, overlooking floating point precision issues can cause trouble. Comparing floating point results directly is unreliable due to potential inaccuracies, so always account for a small tolerance when making such comparisons. Another common challenge is implementing an inefficient brute force solution. Generating all possible parenthesizations without pruning invalid or redundant cases can quickly lead to exponential runtime. Optimizing your approach with techniques like memoization can save significant computation time by avoiding redundant calculations. From an interview perspective, there are key insights to keep in mind. This problem is closely related to the optimal parenthesization or matrix chain multiplication problems. Recognizing this pattern can help you identify dynamic programming as a likely solution. The problem also exhibits overlapping subproblems and optimal substructure, which make it well-suited for dynamic programming techniques. During interviews, it's crucial to clearly articulate how you break the problem into subproblems. For example, you might identify the optimal strategy as something like maximizing the left partition while minimizing the right. Finally, be prepared to discuss trade-offs between different approaches, such as brute force, dynamic programming, and greedy heuristics, in terms of both time complexity and implementation challenges. The optimal division problem connects to several related problems that can help deepen your understanding of similar patterns. For instance, LeetCode 241, Different Ways to Add Parentheses, involves exploring all valid parenthesizations of an expression, an essential skill for solving this problem. Another related problem is LeetCode 312, Burst Balloons, which is a dynamic programming challenge that also deals with optimal substructure. LeetCode 1000, Minimum Cost to Merge Stones, focuses on minimizing costs under specific merging constraints and shares similarities in the way subproblems are structured. Lastly, LeetCode 1246, Palindrome Partitioning 3, uses dynamic programming and partitioning strategies, making it another valuable problem to study for building your understanding of these techniques. When solving the optimal division problem, it's important to consider alternative approaches and understand their trade-offs. A brute force approach involves generating all possible parenthesizations and evaluating each one. While this method is simple to implement, it's highly inefficient due to its exponential runtime. Dynamic programming, on the other hand, leverages a DP table to store the maximum and minimum results for each subarray range. This method is much more efficient, with a time complexity of O(n cubed, but requires careful handling of state transitions and indices. Memoized recursion offers a middle ground, using a top-down approach with memoization to avoid redundant computations. While easier to implement than dynamic programming, it can be less space-efficient in certain scenarios. Finally, greedy heuristics can be applied by using domain-specific rules to prune the search space. However, this approach may not always guarantee the global optimum, making it less reliable in some cases. Each approach has its own strengths and weaknesses, and selecting the right one often depends on the problem constraints and the context in which you're implementing the solution. Great job! In this session, we covered the optimal division problem, highlighting key concepts like recursion and optimization strategies. Remember, practice is key, so keep solving similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!